All right. So my microphone is off. Is it okay? Yeah, you can ask if it goes from here, but I think they do. Okay. Good. So hello everyone. I'm Peyman. I was asked to explain a little introduction to linear differential equations because I guess you guys are not taught in chemistry department. But so this is a very oversimplified introduction because most of the mathematicians spend their life on differential equations, special partial differential equations. So I just put a very simple introduction here. So let's begin. In mathematics, we try to explain the relation between different actually parameters and variables in something that we call equation. The explicit equation examples are like Newton's second law or mass energy equivalence, which are really famous. But this kind of explicit definition and relations, unfortunately, are really rare because nature and reality they are really complex. So we have no choice to define the relation based on rate of the change of variables. If an equation contains the change or rate, whether with respect to time or location, we call it the differential equations. The famous examples is the fixed second law, which is describes diffusion with respect to time and location, and also Schrödinger equation. In Schrödinger equation, as you probably all of you have maybe noticed, some part of the Hamiltonian actually contains the differentiations which explain the location of the electron. So in most cases, we cannot solve these equations directly. We cannot find that function that satisfies the restriction explained by the equation. So we need to use numerical method. But before going into the actually some details about the solution, I need to define some terms and definitions here. So first thing is order. Order is the highest derivative that is mentioned in the equation. For example, in the first one, the order is the first example explains the first order equation, and because it only contains the first derivative, and the second one is of course the second order because it includes the second derivative. The second term is degree of the equation. The degree is the highest power of the highest order in the differential equation. For example, in the example that I mentioned here, the order is 6 because the highest order, the highest derivative is 6, but the degree is 4. And we have other definitions, ordinary differential equations and partial differential equations. Ordinary differential equations only includes one independent variable. For example, in these examples, which shows the second order equations, the only independent variable is x, which y as a function depends on x, which is only one variable. But in partial differential equations, we have multiple independent variables. One example is diffusion equation that depends that concentration C depends on time and also location. And a solution is a function that satisfies restriction defined by the differential equation. So our goal in differential equation is to find that function, which in most cases we have no choices using numerical methods. But here I want to find the direct solution based on the algebraic functions. So first order systems of differential equations actually are type of equations that we can find the explicit equations as solution. The general form is the system of the differential equations that in which the variable is explained by different function, and we only have one independent variable, which is t. But for finding the explicit solution, we need to oversimplify this general form, which in next step is explained as linear system. In linear system, there is no multiplication of the functions. For example, as you see, in the linear system, we cannot see any multiplication between x1, x2, etc. So we, as I mentioned some examples here, examples of linear system, as you see in the first example, that has constant coefficients, and we easily can solve this equation. As you see, the x and y are explicitly expressed explicitly as trigonometric equations. But in the second and third example, as you see, for example, in the second one, it is still a linear system, but as you see, the coefficients are not constant. We can see the t as an independent variable in the coefficients. And also in the third example, as you see, it's not even the linear system. We have a multiplication of the different functions. And the solution of these systems are very complicated. We cannot find the explicit solution for these things, so we have no choice for numericals other than numerical solutions for these systems. Here, I only focus on the linear first-order systems. So linear first-order system, as I mentioned, can be explained in the matrix and vector representation. If the B vector is 0, we call the system homogeneous first-order system. So it's another step of the simplification of this system, but also solving this system is also kind of complicated. At the last step, we oversimplify the system as a system with the constant coefficients. So A matrix is not dependent on the t variable, and all the coefficients are constant numbers. So at this stage, we are able to solve this system based on the steps that I'm going to explain. So first of all, we need to find the eigenvalues of the A matrix, which is based on the first we need to solve the determinant of the A matrix minus lambda identity matrix. By solving this equation, we obtain the lambda, which explains the eigenvalues. After we obtain the eigenvalues of the system, we can actually obtain the eigenvectors. Having these both parameters, we can explain the solution of the system based on the following, based on the equation that I mentioned at the bottom of the page. The system easily can be explained as the summation of the exponential function multiplied by eigenvector. So in the following slide, I put an example. So as you see in this linear system of the equations, A matrix, as I said, it includes all the it's only it's actually A matrix the constant values. So first of all, we determine the lambda values based on the these determinants, and then after we obtain the lambdas, which here it's -1 and 4, we easily can calculate the eigenvectors, and based on the previous equation, we easily can explain the solution of the linear system. But there is one exception, because in some cases, lambda could be complex. For those who do not know the complex numbers actually are numbers that contains the negative square of 1. So we represent the negative square of negative 1 as I. So if you solve the determinant and obtain the complex number, we need to add some trigonometric functions to our solution. So beside that exponential function, we need to actually multiply trigonometric functions for obtaining the solution. And it's based on the following steps. So lambda is expressed as alpha plus I beta. As I said, I is the square of the negative 1. A square root of the negative 1. And the eigenvector is explained at R and S. The general solution of this system is expressed as the following equation. So first of all, for this example that I mentioned here, I obtained lambda, which is -2 plus minus I, and which means alpha is -2 and beta is 1 here. Then, based on the lambda, I obtained the eigenvectors. And following the equation, we can easily find the solution of these linear differential equations. So I guess that's it. Please let me know if you have any questions.
Okay, please join me thinking. So any questions, especially from those who yet look forward to take differential equations? Or maybe catching any errors from those who think them? Even
finding the eigenvalues, that's using the Wronskian, right? Or is the Wronskian something else?
Using what?
It's called the Wronskian.
Wronskian?
Yes. Wronskian.
I'm not sure what you're referring to, but you're asking about how to calculate the eigenvector?
Yeah, it's taking the determinant.
So eigenvector, let me show the equation. I think it's so here, as you see, determinant a minus lambda I. The next to it is another equation.
Yeah.
So after you calculate lambda, you can use this equation for calculating the vector, the eigenvector. Is that your question?
We looked it up. The Wronskian is something else. It's two equations. Thank you, though.
questions? I do have one type, but I can verbalize. So in your last slide, you showed that solution for system of ordinary differential equations with constant coefficients may have exponentially growing or exponentially decaying character, or it may have oscillatory or combination of both. Right. So which properties of the A matrix you tell us for sure that it will be only decaying or only growing or only oscillating? Just intuitively, it's not a...
Oh, that's a great question. So which one is related to decaying and which one is related to harmonic of the A matrix? So as I see
because your example clearly shows it.
So the lambda, of course, is related to the decaying, but I'm not sure.
Okay, what about, if you can say about the matrix, can you say something about eigenvalues? Which eigenvalues provide oscillatory solutions and which eigenvalues provide growing or decaying solutions?
The eigenvalue is directly related to the exponential function. The values
yes,
that are
yes, but it's like imaginary exponential oscillates.
Yes,
I'm talking about real exponential which grows or decays.
Oh yeah, of course, based on this equation, so of course alpha which is the first part of the real part of the actually eigenvalue, explain the decay, and the imaginary part explain the harmonic.
Okay, so if all eigenvalues are imaginary, then it will be only harmonic.
It's only harmonic.
That's further behavior. Correct. And if all eigenvalues are real, then it's only growing with the exactly. So this property will be observed in the solution that we find numerically. More questions for Peyman? Questions? 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 Thank you.